Sir, we'll be starting the session.
Okay.
Yeah.
Okay.
So, greetings to all participants and to our guest speaker. So, I'm Anupama Thakur, and I welcome you to the another episode of IEEE Virtual Talk Series 2020. And we are grateful enough that we have with us Dr. Koharan. He's from Turkey. So, I'll be formally introducing our speaker to all the participants. So Dr. Koharan is a native from Turkey, and he received the BS degree in Electronics and Communication Engineering from Turkey in 2008 and MS degree in Electronics and Communication Engineering from Turkey again in 2011 and PhD degree in Electronics and Communication Engineering from Kadir Has University at Istanbul, Turkey in 2016. Since 2018, he has been an assistant professor with the Electrical Electronics Engineering Department at Trakya University, Turkey. He is the author of over 30 articles, 5 book chapters, and 1 book in Turkish. He serves several editorial positions in Springer, elsewhere, IEEE books and journals. His research interests include wireless sensor networks, wireless communications, statistical signal processing, indoor positioning systems, power electronics, and 5G. He is also the editor of Turkish Journal of Electrical Engineering and Computer Sciences, and he has many awards and honors to his credit. And he has been into various leadership positions in IEEE as well. And I'm happy to inform you that he's also the senior member of IEEE. So with this brief introduction, I welcome you, sir, for your talk. Yes, sir. Over to you.
Okay. Is it visible and can you hear me, everyone? Is there any problem?
Yes. Yes, we can hear you, and the presentation is also good. We can start.
Okay. Okay, thank you for introducing me. I'm Dr. Koharan Cengiz from Turkey, Edirne, Trakya University. Also, I'm a senior member IEEE, and also I'm global advisor of IEEE student branch in Trakya University. We are always with my students for making good events together. Now, I will present you energy efficient protocols for wireless sensor networks. This is my PhD topic. In my PhD, I designed a wireless sensor network protocol, especially it works in network layer and its routing protocol. It tries to find energy efficient solutions to the wireless sensor network. So our presentation consists of motivation related work and our design protocols. We designed 2 protocols in my PhD: low energy fixed clustering algorithm LEFCA and multi-op LEFCA, its extension. And I will show you some simulation results, some conclusions, and also I will explain here some future aspects and some research opportunities for young researchers. So as a motivation, you know that wireless sensor networks are widely used in various fields, thousands of fields, especially nowadays it is very important that they are used in healthcare systems and also in disaster relief, target tracking, environmental control, smart cities. And to distribute the sense data in wireless sensor networks, we have 3 main approaches: direct transmission, multi-op routing, and clustering. In direct transmissions, sensor nodes individually transmit the measured data to the remote base stations. In multi-op routing, sensor nodes are utilized as relay nodes, and sensor nodes transmit the collected information to the remote base station by using other sensor nodes. And finally, in clustering, there are some clusters, and cluster heads are responsible to collect information from the members and then transmit this information to the base stations. So we know there are some problems in clustering topologies, clustering protocols, especially 3 main problems are here. increase in energy consumption, decrease in network lifetime, and also there are some additional network overhead. So our proposed LEFCA, the novel protocol, aims to solve the issues by using fixed clustering and also changing the cluster head election process of the known protocols. So, as a related work, the most famous protocol is Leech, and it has two main phases, setup phase and the steady state phase. In setup phase, in Leech protocol, cluster head election, cluster head advertisement, and also cluster formations occur. And then in steady state phase, the data transmission to the remote base station is occurred. But in Leech protocol, these steps are done again and again, and it causes to additional energy consumption and also network overhead, network traffic. So we aim to use fixed clustering approach to solve the issues of Leech and Leech-based protocols in LEFCA protocol. I will explain in details in further slides. So there are a lot of extensions to the Leech protocol in literature. You can find thousands of protocols, and they mainly try to solve the problems of Leech by changing cluster head selection mechanism, by determining cluster heads according to the remaining energy of the nodes, sensor nodes, and by using fixed clustering. So we decided to use fixed clustering to solve the problems of Leech-based protocols in the literature. Leech-F is also an extension to Leech, and it is also fixed clustering approach, and we can say that it is near to our idea, but there are some differences, and also our protocol has some novelties. I will also explain it. So here also there are some another extensions, some another studies in the literature. For example, Leech, it has a novel idea. DEEC protocol, stable protocol. It's also famous and most known protocols in the literature for wireless sensor networks. And also Lemma is another kind of protocol. iLeech, pLeech. A lot of protocols you can find when you look at the literature. So let's talk about LEFCA in details now. Our proposed LEFCA protocol aims to use fixed clustering approach and determination the cluster heads by using the base station approaches together. So it has a combination while finding the clusters and also while determining the cluster heads. And also it uses intelligent cluster head determination mechanism, and it tries to elect the nodes that are almost at the center of their associated clusters at the beginning of the algorithm. And in most protocols, all of the protocols, the cluster heads are determined randomly at the beginning. But in our LEFCA, we aim to determine them by using an intelligent smart cluster determination. And also we made some simulations about that, and we saw that intelligent cluster head determination of LEFCA provides additional energy savings. At the beginning, by doing this, we obtained approximately 10% energy savings. I will show them in the results. So LEFCA has intelligent cluster determination, and also it uses a threshold-based cluster head change mechanism. And this part is very significant for LEFCA. It aims to abuse the energies of the cluster heads before determining a new cluster head. And this idea is not proposed in any of the existing algorithms, and this part is the novel part of LEFCA. Also, I will explain this part in details by some mathematical derivations. So again, for approximately all protocols in a wireless sensor network, LEFCA has setup phase and the steady state phase. In setup phase, we determine the clusters, and then we determine the cluster heads, and then cluster heads try to collect information from the cluster members, normal sensor nodes, and then in the steady state phase, our data transmission job is done. But in setup phase, as you see that our protocol is fixed clustering protocol. So in the setup phase, we form the clusters only once, and then our clusters remain constant. They are not changed. So we make the setup phase only once. Therefore, we obtained additional energy savings, and also we obtained significant network overhead, network traffic improvements by using LEFCA protocol. So this figure shows the setup phase of LEFCA. At the beginning, we determine the cluster heads by using our intelligent cluster head selection mechanism, and then our cluster heads broadcast advertisement messages to the members. They say that I'm cluster head, and then these members transmit join request messages in the network, and they try to join the nearest cluster heads, nearest associated cluster heads. Then, according to number of members in each cluster, cluster heads provide TDMA schedule messages to the members. And then, in this TDMA schedules, our cluster heads, cluster members transmit their information. For example, here we have a TDMA schedule, TDMA frame. For example, we have 10 members and one cluster head. Here we will have 10 time slots for members and also one additional slot for cluster head. In these slots, each member transmits the measured information to the cluster head, and then finally, this cluster head will transmit the combined message, gathered information to the base station, and then for each cluster, this process will be done, and then our one round will be completed. So in a one round, our sensor nodes measures the environment, and then they send this measurement to the associated cluster heads, and then these cluster heads transmit this collected information to the base station, and then one round is completed. For the second round, the same things are done again and again, and LEFCA works like this. So in data transmission phase, the data collected information is transmitted to the base station, but sometimes we need to change the cluster heads, because as you remember at the beginning we said that we abuse the cluster heads. For example, in our network, let's imagine that we have a field. For example, we are making temperature measurements, and we have a field. It has dimensions 100 meters to 100 meters square field, and we randomly deployed the sensor nodes, for example 100 sensor nodes, and let's think that we have 8 or 10 clusters. In each cluster there are cluster members and also there are cluster heads. So the cluster heads at the beginning are selected by using the intelligent cluster selection mechanism, and for example each sensor node has 2 joules initial energy. So you know that we aim to abuse the remaining residual energy of the cluster head. Therefore, in here our cluster heads are abused, and we use them, for example, for a lot of rounds. For example, 400 rounds, 1000 rounds, and then we should determine a new cluster head. And so while we are determining this, we use the threshold-based cluster selection mechanism. Here, we have to determine the cluster head according to its remaining energy. And according to our threshold value, for example, we check its initial energy. For example, its energy is 2 joules, and then it becomes decreasing, and then, for example, it becomes 0.20, 0.40, and then we decided to use a new cluster head. Here, how can we define this threshold value? This equation is very important for us. This equation shows the energy dissipation of a cluster head for a 1 round, and here this part is very important, distance to base station part. So as you see, it has the fourth power of the distance. This fourth power or second power is directly related with the distance between base station to the cluster head. For example, for our case, this distance, the critical distance, crossover distance, is approximately 87 meters. So if our cluster head's distance is greater than 87 meters, we should use this equation, and its energy will be reduced by the fourth power of this distance. If that distance is lower than 87 meters, then this fourth power will become second power. So therefore, the distance to the base station is very, very important parameter for us. So by using clustering approaches to sensor networks, we are trying to get rid of this fourth power. But here, to finding the proper, suitable, especially suitable threshold value, we imagine the worst case situation in here. So by using this equation, we thought that 100 sensor nodes, and there is only one base station here. It is remote base station, and we thought that there are one cluster head. There is one cluster head which is at the origin of the field, and it is remotest node to the base station. So here we thought that, for example, we have 100 members and we have only one cluster head, and therefore 99 members will be just sensor members, and they will try to send information via this cluster head. So for this case, for 1 round, we try to calculate that one cluster head will consume how much energy. So by using functions, we found this value is approximately equal to 0.005 joules. So for 1 round, for the worst case, our cluster head will consume this amount of energy. So then, as you know, we are trying to abuse the cluster head's energy. So we decided to determine as 0.05 joules in Lefka protocol. But here, it can be dynamic. There is no problem. We can increase, decrease this value. But if we decrease, it will be critical, because we can face network connectivity problems, and especially for critical applications, especially for healthcare applications, earthquake measurements, fire measurements, you always want to collect information from the field. Therefore, this value should be equal to this value or should be greater than this value. Therefore, we obtained for our parameters, its value is according to our calculations 0.05 joules of 2 joules. So we start with cluster head with 2 joules and we abuse it until its energy becomes 0.05 joules in left upper. So also, is there any problem? Can you hear me? Is it visible? Is it okay?
Yes, sir.
Yes,
You're
sir.
loud and clear and it's visible.
Okay, I'm going on. Now, the second part of our presentation is about Maltop Lefka. Maltop Lefka is extension of Lefka. It has some additional features and some novel things. And in Maltop Lefka, our Maltop Lefka protocol was published in IEEE Access Journal. You can also find it and you can see the details of the publication, and also you can contact with me. Top Lefka, I will summarize it in a figure. These are some additional information. It has same properties for cluster head selection, for TDMA message part, for determining the cluster heads. They are all same, but the novelty is now. Let's think that we have a small wireless sensor network, and here we have 4 clusters. And for each clusters, we have one cluster head, and here we have remote base station. Now, in original Lefka, as we know that our member nodes will collect information from the environment, and then we'll send this information to the associated cluster heads. For example, for cluster 1, it is 5. For cluster 3, it is 15. And then, in original Lefka, these cluster heads will transmit information to the base station individually. For example, 5 will send the information to the base station, 15 will send, 11 will send. But in Maltop Lefka, in our new protocol, these cluster heads will be used as relay nodes. And then, for example, while 5 is trying to transmit information to the base station, it will use the nearest neighbor cluster head as relay node here. So it will use 11. And then 5 will send the information of its cluster to the neighbor cluster at 11. And then we'll send this information and also we'll add its own clusters information into that, and then we'll send whole information to the node 20. And finally, as you see from here, 20 receives information from 11 and also from 15. And as you see from this figure, it has whole information to this network, and then it will send the whole information from the information of cluster 1, 2, 3, and also its own cluster to the base station. Now, this provides us some additional energy savings. We will see in the results part, but there are some problems here. For example, there are a lot of network load on node 20 on this cluster. So how can we solve this problem? It is still open issue. So with researchers for master or for PhD or for postdoc researchers, we can study about this topic. And also, if any problem occurs to node 20. If any failure occurs, or if it becomes out of battery, or if there is any connection loss, what will be happen? Because we will lose all information about the network. So if we have here critical application, it will cause to critical problems. So this is also another open research issue for MLEFCA, multi-op LEFCA. So again, we can discuss these problems with researchers. So they can join me and they can contact with me via email and Facebook, and we can discuss about these problems. So let's see some simulation results. As you remember, we said that we can determine the cluster heads randomly or by using intelligent cluster head mechanism. So this figure shows the difference between random selection or intelligent cluster head selection at the beginning. As you see, intelligent cluster head selection provides additional energy savings. Therefore, we decided to use intelligent cluster head selection in original LEFCA and also multi-op LEFCA. And the impact of threshold value. As you remember again, we said that we can change threshold value because it can be dynamic, there is no problem. And this shows what will happen when we increase or decrease the threshold value. As you see from the figure, it is better to use lower threshold value, but as you remember again, we said that it is very critical. We should be careful while determining the threshold value in LEFCA protocol. Also, to track the status, energy status of the nodes, sensor nodes, we obtained the energy map of the network. Here, this shows a snapshot from LEFCA round. This is LEACH, the original protocol in the literature. It is found in 2020 by Wendy in MIT in her PhD. And this is LEFCA. As you see from LEACH, there are a lot of dead nodes. In our termination, dead nodes becomes the nodes that are become out of battery. So here, but LEFCA has some dead nodes, but there are a lot of aligned nodes. So therefore, as you see, we can collect information from all parts of the network. And in LEACH, we cannot collect information from the remote regions of the wireless sensor network, but in LEFCA, we can collect information from whole part of the network. So for critical applications, LEFCA becomes suitable, especially for healthcare applications and especially for earthquake measurements, especially for fire measurements. This is another snapshot for the further rounds. Again, we can still collect information by using LEFCA protocol. This value is 4,600 rounds. It means that we transmitted information for 406 rounds. We got measurements for 406 times from the environment, from the network. So the remaining energy of the protocols, here you see that LEACH, LEACH-F, MOD LEACH, DEEC, SEP protocol, and LEFCA. As you see from the figure that LEFCA provides the best energy efficiency performance when we compare it with existing approaches. Also, it has, as you see, robust nature from the figure. As we see that, it has robust nature and it has very good distribution about the energy, but it has non-linear nature, as you see from the figure. So when we check the number of alive nodes according to node rounds, as you see, Lefka provides the best performance, and it has approximately a linear nature, and also again it has very robust performance when we compare it with other protocols. These are some numerical results. For example, how can we obtain them? Average lifetime and maximum lifetime. We generated sensor network randomly for 100 times, and we called that iteration. And for each iteration, we conducted all protocols in MATLAB, and then we obtained the results, the lifetime results, and then according to this 100 iterations, we obtained the average lifetime results of the protocols and also maximum lifetime results of the protocols. And these are the initial energy values of the protocols according to nodes. For example, as you remember, in our protocol, we have 2 joules initial energy for each sensor node. And this is a very interesting and significant result. This result shows the total data transmitted to the base station. In some publications, you can see that it is said that throughput, but throughput is different from this manner, because throughput corresponds to useful data transmitted to the receiver. But here we are just talking about packets, because we study network layer. Therefore, this shows some packets transmitted to the base station, and Lefka provides a lot of improvements when we compare it with other protocols. So we obtained some additional results for different number of nodes, different number of especially different number of cluster heads and different field dimensions. These are some additional results, and also we tried to obtain the results for what will happen when we put the base station inside of the sensor network, at the origin of the sensor network. And also these are the comparisons with Maltop Lefka and Lefka. For some, approximately Maltop Lefka provides 5% or 10% improvement when we compare it with Lefka, but it can enhanced and improved. So again, we are open for collaborations with researchers. And as a conclusion, we talked today about Lefka and Maltop Lefka. I'm trying to explain in details the idea behind Lefka and Maltop Lefka. For Maltop Lefka, there are some problems, as I mentioned before, and also in addition, at the beginning of the determination of the cluster heads, some machine learning or deep learning solutions can be applied to Lefka or Maltop Lefka, and also some additional ideas can be applied to Lefka and Maltop Lefka. And finally, for Lefka and Maltop Lefka, we can use some additional solutions, especially for mobile situations, because these are fixed clustering approaches. And what will happen if our nodes become mobile? What will happen if we apply Lefka or Maltop Lefka to 5G networks, 4G networks, the mobile users with cell phones? What will happen? So these are also can be applied to Lefka and Maltop Lefka protocols. thank you for listening. So if any questions, we can talk about.
Yes, thank you so much, sir, for sharing your research
You are
and your
welcome.
knowledge. Yeah. So now the session is open, and I request the participants if they have any question. So either they can post in the chat box window or they can unmute themselves.
Okay.
Yes. So any
And
question?
any question?
Hello.
Hello.
Good evening, sir.
Good evening.
This is Atul from Maharashtra.
Okay. Nice to meet you.
Sir, my question is that clustering in my base, if I think it's overhead to the wireless networks. Okay, because every time you have to select the group head or cluster head.
One sec. I'm coming. Okay. Sorry for it. There was some noise. Can you please ask your question again?
The overhead for the networks, because every time you have to select the head or to check the energy level of the nodes like that. So is there
Okay.
any alternative ways in the wireless sensor networks where we can communicate? We have not to communicate to the base station every time, because if we don't have any clustering like that, so we have to go to the base station every time when we need some data.
Actually, yes, you are asking a good question, and there are some problems about that. I understood you, but as you know, we use fixed clustering approach, and just we are collecting the energy levels of the cluster heads. Cluster heads, while sending the collected information to the base station, it only adds some parts to the message, and it just sends its remaining energy for that round. So we can do it while sending the measurements, and it won't cause to a lot of network overhead. But if we collect all the energy levels of the nodes, then it will be a problem, because it will cause some additional network overhead in the network. But we don't need to collect energy levels of the node. But in Levka, we have some additional protocols, and they are also they were also published in some IEEE conferences. For example, we have MESA protocol, multiple maximum energy selection algorithm in Black Sea COM IEEE. It collects the energy levels of the node, and then while determination of the new cluster head, it determines the new cluster head that has the maximum energy. But in original Levka, we determine the new cluster head by randomly. Also, we have another idea, that is the nearest node to the existing cluster head approach, nearest cluster head selection algorithm approach. And in that approach, we should collect the distance information from the members. But original Levka does not need this information, because it just randomly select the members, and we just need the energy information of the existing cluster head, current cluster head. So I think for original Levka, there is not a lot of network traffic, especially energy consumption problem for this manner. Okay.
Yes, I hope Atul sir, it's clear to you.
Yeah,
If
yes,
you
ma'am.
have,
Yes.
Yeah, if you have any
Okay.
further questions, so you can ask to sir again.
Yes, for any questions, and also you can contact me with LinkedIn, email, and Facebook. I am always open your questions and
Hello, sir. I have a
collaborations.
question. Sir, I have a question.
Yes, yes.
Hello. Yes, I am Siddhartha Chatterjee from JS Group, GMIT, India. So my question is, sir, for lightweight communication purpose, LEFCA is sufficient or suitable? Suppose I want to send one information from A node to B node from any type of lightweight communication purpose, LEFCA protocol is sufficient or suitable, or other types of network is suitable?
Light wave, you mean?
Yes, sir.
Visible light communication, as you mean.
So lightweight communication purpose, lightweight.
It can be applied. We have just problems for
So wait,
mobile
I
environment.
request participants to mute.
Okay, thank you.
Okay. It can be applied. There is no problem. We just problems for mobile environments because our protocol is a fixed protocol, and we designed our protocol especially for healthcare applications, especially for earthquake measurements and fire rescue. As you know, for example, in fire rescue, you track the known place, you put the sensors, and then you try to collect information for sometimes in a day, especially for summertime in forest. But what can we do for mobile environments? It will be a problem, and this problem can be solved by new researchers. Therefore, I'm open for collaborations with you. Maybe you can make a master and PhD, also postdoc with me in Turkey, and we can study for that, and also for future networks, as your question, and also heterogeneous networks, 5G networks, and for another network applications, and also maybe we can make some software defined networking additions for LEFCA protocol. So we can, I think, have new publications and new research ideas from LEFCA and Maltop LEFCA. It has still some problems that should be solved. Waiting for your new ideas, and we can talk about that. Okay, any more questions?
Yeah, so Siddharth sir, I hope it's clear to you. If any further question, then you can ask sir.
Yes.
Sir, thank you for your answer.
Okay.
Welcome.
So thank you. So sir, there's one question in the chat box window. Could you please see it, or shall I read it for you in the chat box window?
Okay.
Yeah.
Thanks for talk. Can you highlight wireless sensor network issues and advances in distributed temperature sensor? Do you mean that question?
Yes, sir. Yes, sir. Yes, sir. This
Yes.
question.
Okay. Yes, we have, especially in wireless sensor network, the main problem, the major problem is energy efficiency. Because, you know, the wireless sensor networks has the devices, sensors, which have restricted energy. So, for all protocols, the main purpose is to provide energy efficiency, to increase the network lifetime. So therefore, we should especially motivate on energy issues. And distributed temperature sensors and another new type sensors can be used. And some problems can be also solved by using additional hardwares. But we should look at the cost, because when you use, for example, 1,000 sensors, 1 million sensors, what will happen? So you should check, you should look at also the cost. You should make cost analysis for it. Some additional sensors, maybe we can increase the coverage of the sensor nodes, because there is another problem about the coverage. The sensor nodes has restricted coverage, and they cannot reach to remote base station or cluster heads or some gateway nodes. So by using fiber optics also, the distances, the restricted distances can be increased. Therefore, some additional hardwares, some problems of sensor networks can be solved, but in that part, you should make further and deep analysis about cost. Okay? Any more questions?
Yes, thank you, sir. So,
You are
any other
welcome.
question?
Okay, we can take last question if they want, and then here also I can
So you can write your email address in the chat box.
yes, here I can type it.
Yeah.
Sure.
So one thing I would like to ask you, sir, like not ask, I would like to
Sure.
have your comments. Yeah. So,
Sure.
sir, like you have worked so much in this area and in this domain. So, what recommendation you would like to give to the Indian participants who have joined today, like on this domain, like what what opportunities they can have in this area? So, any
Okay.
recommendations to the participants who have joined?
Okay, this is good question. Especially for wireless sensor networks, I will be honest about it. It is very hard topic because there are a lot of studies in this field. So the most known problem: how can I find the open issue? How can I find the novel thing? So this is the main problem. But also there are a lot of sources, papers, books, presentations, additional documents. So you can learn a lot of things while studying about sensor networks. But for future aspects, I recommend them. They can use machine learning or deep learning solutions to wireless sensor networks. This is the first thing. The second thing, especially software-defined networking nowadays is very famous. So they can apply software-defined networking to wireless sensor networks. This is the second thing. The third thing, cognitive radio networks is very related with sensor networks. So they can use cognitive radio solutions. And for these days, especially, as you know, 5G is very promising research field. So they can study for mobile applications, mobile parts of sensor networks. Because in 5G networks, we will have very huge, very big heterogeneous, and it will have trillions, billions of users. So therefore, using mobile applications, using mobile solutions to wireless sensor networks, and then applying them to heterogeneous network in 5G will be good research opportunities and research fields for the researchers.
Okay, yeah. So thank you so much, sir. So I
You
hope
are
the
welcome.
recommendations you have mentioned will largely help all the participants to keep all these considerations in mind while working in this area. So now, sir, I would like to request you to stop sharing your screen now,
Okay.
and we can have a group picture with all the participants who have joined
Okay.
today. Yeah.
Oh, sorry.
So yeah. So I request all the participants, they can turn on their videos. and we can have a group picture with sir. Yes, to make it more memorable. Yes, I hope no more further questions are there from the participants. Yeah. So I'm waiting for the participants to turn on their video. Anyone else joining us?
Present, ma'am. Anupama, ma'am. I'm Siddharth Chatterjee, present. I'm traveling
Yeah.
actually.
Yeah.
Yes, ma'am. Yes,
Thank you so much, sir. Thank you so much, sir.
yes,
Thank
yes.
you. Is anyone else? Want to, join us in the picture? So, okay. So I thank our speaker and all the participants who have joined us. So thank you for spending your Sunday evening with all of us. And I thank sir who has joined us from Turkey. So thank you so much, sir.
You are welcome.
Yeah, it
You're
was a
all welcome.
very valuable session. So thank you, take care, and thank you all participants for joining us. Okay, sir, take care. Thank you so much.
Okay. Is it finished?
Yes, sir, it is finished now.
Okay.
I'm ending the meeting and
Okay.
I'll connect
Keep
with
in
you later,
touch.
sir. Yeah,
Yes,
thank
keep
you
in
so
touch.
much, sir.
Okay. See you
Thank
later.
you.
Bye. Thank
See
you
you.
for listening. Bye bye.
Yeah, thank you, everyone. Take care.